Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics, Delhi University. Today we are going to discuss about a module called birefrigerants in nonlinear optics. This belongs to the paper Characterization of Materials 2. So students, let us see what we are going to learn in this module. We will see the introduction to second harmonic generation, and we will study the details of phase matching, and finally we will study about the birefringence. The second harmonic generation, also called the frequency doubling and abbreviated as SHG, is a nonlinear optical process in which photons with same frequencies interact with a nonlinear material combined to generate new photons with twice the energy and hence twice the frequency and half the wavelength of the initial photons. Here the dipoles oscillating with the applied electric field of frequency omega radiates electric field with frequency 2 omega as well as frequencies of omega. In second harmonic generation, the applied and driving field at frequency omega produces nonlinear polarization at frequency 2 omega. The total SHG field generated at point R is the resultant sum of interacting waves generated between the edge of the medium at R is equal to 0 and R, which is given by E2 is directly proportional to epsilon 0 chi 2 E1 square omega 2 square multiplied by e to the power 2I bracketed k2r minus omega 2t bracket and integration from 0 to r e to the power I bracketed 2k1 minus k2 and bracket r0 and dr0, which is equal to epsilon 0 chi 2 e1 square omega 2 square multiplied by e to the power 2I k2r minus omega 2t multiplied by e to the power I 2k1 minus k2 times r0 divided by I multiplied by k 2k1 minus k2 end bracket. This SHG frequency omega 2 and wave vector k2 is related to the wave vector and frequency k1 and omega 1 of the fundamental by k1 is equal to n1 omega 1 divided by c, k2 is equal to n2 omega 2 divided by c, and since omega 2 is equal to 2 omega 1, we can write k2 is equal to 2 n2 omega 1 divided by c, where n1 and n2 are the refractive indices of the medium at frequencies omega 1 and omega 2 respectively. Phase matching. The phase matching of the radiated electric field of frequencies omega and 2 omega is critical in second harmonic generation. They have to be in phase to favor constructive interference, and the applied electric field should be strong enough to generate the second order radiation, but not so strong that the first order term dominates. So, we could think of SHG signal as a perturbation, and
the lights of two frequencies should be added and should not cancel each other. Considering the wave propagation in the positive g direction, the total output is a sum or the integration of all dipoles at every position in the material, and mathematically can be written as eta is equal to 1 divided by L square integration from 0 to L e to the power I to k omega g e to the power minus I k omega dg square, which is equal to 1 divided by L square integration of 0 to L e to the power I delta k dot g dg square, which is finally equal to sine of delta k L divided by 2 whole divided by delta k L divided by 2 whole square, and the second harmonic intensity at G can be expressed as I to omega is directly proportional to I omega square 0 start bracket sine delta k dot g by 2 divided by delta k dot g by 2 stop bracket and square, where I omega 0 is the incident intensity, so the maximum intensity is achieved for identical phases. This function has a maximum for delta k dot g is equal to 0 and delta k dot g is equal to 2n pi, indicating that the condition for most efficient SHG is delta k is equal to 0 and is termed as phase matching. The output of the second harmonic intensity could be written as a sine C function and is given by sine C delta k dot L by 2 is equal to sine delta k L divided by 2 whole divided by delta k L divided by 2 whole square. Many phase sensitive nonlinear processes, especially the parametric processes, including frequency doubling, sum and difference frequency generation, and parametric amplification and oscillation, require phase matching to be efficient. For optimum nonlinear frequency conversion, it is required to have proper phase relationship between the interacting waves maintained along the propagation direction. This condition is fulfilled when the amplitudes from different locations are all in phase with the resultant total wave at the end of the nonlinear crystal. An effective nonlinear interaction is possible with phase mismatch close to 0. The phase matching of frequency doubling is given by delta k is equal to 2k1 minus k2 is equal to 0 where K1 and K2 are the wave numbers of the fundamental and second harmonic beam respectively. Without chromatic dispersion, K2 is equal to 2K1 would hold so that the phase mismatch vanishes. In figure 1, the arrows indicate the phase corresponding to the amplitude contributions from different parts of the nonlinear crystal to the harmonic wave. These contributions aided constructively only when the phase matching is achieved and results high power conversion efficiency. Else, the direction of energy transport changes periodically with the change in phase between the interacting waves during passaging through the crystal. The energy then oscillates between the waves without being transferred in a constant direction. The effect on the second harmonic power conversion in a crystal along the propagation direction is demonstrated in the figure. Here, the solid curve is observed during phase matching that indicates growth of power proportional to the square of the propagation distance. The dashed curve represents the power during non-phase making with the second harmonic power oscillating between 0 and a small value. Effect of temperature in the SSG power efficiency. The crystal temperature around the optimum point develops phase mismatch and variation in the conversion efficiency. Figure 3 plots the second harmonic power versus temperature deviation from the optimum point with homogeneous temperature distribution in a crystal. The high conversion efficiency is inversely proportional to the crystal length and also relies on the temperature dependence of the refractive indices involved. Similar relationship applied to other nonlinear frequency conversion processes. Similar curves are obtained, such as for critical phase matching when the angular orientation of the crystal is varied. In practice, the phase matching curve is not as symmetric as shown in figure 3. For example, it becomes asymmetric if the crystal temperature is not homogeneously distributed throughout the length or lower in temperature values at the end faces compared to the middle of the crystal. The temperature homogeneity in a crystal could quantified from the phase matching curve, and the conversion efficiency could be optimized by fabricating crystals of desirable dimension.
Coherence length. The oscillation caused by interference between the SSG waves generated at different points along the path severely limits the SSG intensity unless the phase matching conditions are satisfied. As most of the optical media are dispersive, N1 not is equal to N2. Hence, SSG amplitude oscillates as e to the power I 2k1 minus k2 or with periodicity of LC is equal to pi divided by 2k1 minus k2 along the path. The distance LC is called the coherence length and is typically several wavelengths in condensed media. In a SSG medium, the coherence length is infinite when it satisfies the phase or index matching, and it leads to complete conversion of fundamental into SH. Efficient SSG requires phase matching, which is momentum conservation, satisfying the index matching of n1 omega 1 is equal to n2 2 omega 1. The difficulty in materials is that they are usually dispersive and the refractive index increases with frequency with n2 is greater than n1 in normal dispersion.
Phase matching techniques. The chromatic dispersion of an optical medium is the phenomenon where the phase velocity and the group velocity of light propagating in a medium depend on the optical frequency. Absence of chromatic dispersion could lead to K2 is equal to 2K1 and the phase mismatch vanishes. Due to chromatic dispersion, the wave number of the second harmonic is larger than twice of the fundamental wave. Dispersion generally causes a non-zero phase mismatch as shown in figure 4. Special measures could be taken to avoid this by choosing a different polarization in a birefrigerant crystal.
Now let us study what exactly the birefringence is about. The most common technique for achieving phase matching is the natural birefringerence, generally also called double refraction of uniaxial anisotropic crystals. Birefringerence is the property of non-isotropic material with refractive index dependence on the polarization direction, that is the direction of the electric field, favoring the material capable of exhibiting double refraction by shining an unpolarized light beam. It is referred as the double refraction of light in a transparent molecularly ordered material manifested by the existence of orientation dependent differences in refractive index. These optically anisotropic materials with directionally dependent property are termed as birefringence. This birefringence could be quantified as the maximum difference between refractive indices of the material. Crystals with asymmetric crystal structures are often birefringent. Now, let us study what exactly the isotropic and anisotropic materials and how we can define them. Optically isotropic materials have the properties of identical refractive index in all directions throughout the crystallite lattice. Examples of isotropic solids are glass, table salt, which is sodium chloride, polymers, and a wide variety of both organic and inorganic compounds. The isotropic properties remain symmetrical regardless of the direction of measurement, with each type of probe providing identical results. The term anisotropy refers to a non-uniform spatial distribution of properties resulting for sample materials probed from various directions within the same material. Generally, the observed properties are dependent on the particular probe being used and often vary depending on the phenomena for optical, acoustical, thermal, magnetic or electrical events. Generally, the anisotropic crystals such as quartz, calcite and tourmaline have crystallographically distinct axes and interact with light by a mechanism that depends on the orientation of the crystalline lattice with respect to the incident light angle.
Double refraction. When an unpolarized light beam is incident on a calcite crystal, it usually splits up into two linearly polarized beams. The beam which travels undeviated is known as the ordinary ray or O ray and obeys Snell's laws of refraction. The second one doesn't obey Snell's law, is known as the extraordinary ray and abbreviated as E-ray. The figure 5 represents the schematic diagram for the polarization of light by double refraction. The appearance of two beams is due to double refraction, and a crystal like calcite is referred as a double refracting crystal. The velocity of the O ray is same in all directions. The velocity of E ray is different in different directions. A substance like quartz and calcite exhibits different properties in different directions are generally called anisotropic substance. The axis along which the two velocities are equal is known as the optical axis of crystal. In a crystal like calcite, two rays have the same speed only along the direction. Such crystals are known as uniaxial crystals, where the V0 is equal to C by N0 for O ray and V is equal to sine square theta divided by C divided by NE square plus cos square theta divided by C divided by N0 square is for E ray, where Ne and N0 are constants of the crystal and theta is the angle with the optic axis. C by Ne and C by N0 are the velocities of the E ray when it propagates parallel and perpendicular to the optic axis respectively. Types of birefringent crystals. The first type is uniaxial crystals. The simplest type of birefringence could be described as uniaxial, where the optical anisotropy is exhibited in a single and all the directions perpendicular to it or at a given angle to it are optically equivalent. When the material is rotated around this axis, the optical behavior remains same. This spatial direction is termed as the optic axis of the material. However, for most of the other polarization direction will be partly in the direction of the optic axis and referred as extraordinary ray. The ordinary ray will always experience a refractive index of n0, whereas the refractive index of the extraordinary ray could be between n0 and ne, depending on the ray direction as described by the index ellipsoid. The magnitude of the difference delta n is equal to ne minus n0 is quantified by the birefringence. The second type is biaxial materials. The biaxial crystals are somewhat complex and are characterized by three refractive indices corresponding to three principal axes of the crystal. For most ray directions, both the polarizations would be classified as extraordinary rays but with different effective refractive indices. Being extraordinary waves, the direction of power flow is not identical to the direction of the wave vector in either case. The two refractive indices can be determined using the index ellipsoids for given directions of the polarization. For biaxial crystals, the index ellipsoid will not be an ellipsoid of revolution but is described by three unequal principal refractive indices with values n alpha, n beta and n gamma. Thus, there is no axis around which a rotation leaves the optical properties invariant as observed in uniaxial crystals whose index ellipsoid is a spheroid. Categories of birefringerence. Birefringerence is an inherent property of many anisotropic crystals including calcite and quartz, or it can also arise from other factors such as structural ordering, physical stress, deformation and strain. The naturally occurring materials with asymmetry in direction dependent refractive are referred to have intrinsic birefringence. These materials include many anisotropic, natural and synthetic crystals, minerals and chemicals. Structural birefringerence is used to identify a wide spectrum of anisotropic formation including biological macromolecular assemblies such as chromosomes, molecular fibers, microtubules, liquid crystalline DNA and fibrous protein structures including hair. Unlike many other forms, the structural birefringerence is sensitive to the refractive index fluctuations or gradients present in the surrounding medium. The synthetic materials, including fibers, long chain polymers, and composites, exhibit structural birefringerence. Stress and strain birefringerence arises when the external forces or deformations act on materials that are not intrinsic by refrigerant. For example, stretched films and fibers, deformed glass and plastic lenses, and stressed polymer casting in a naturally isotropic medium by refrigerants can be induced by inhomogeneous mechanical stress. This can be observed by placing a piece of acrylic between two crossed polarizers and applying stress to the acrylic. Colored patterns could be observed resulting from wavelength dependent effect of stress induced by refrigerants. Generally, the optical fibers are not birefringent, but some birefringerants can result from bending that causes bend losses and from random perturbations as observed in bent optical fibers, and also due to thermal effects in laser crystals, which can lead to depolarization loss. Flow birefringence is the one that occur due to induced alignment of materials such as asymmetric polymers that become ordered in presence of fluid flow. Rod-shaped and plate-like molecules and micromolecular assemblies such as high molecular weight DNA and detergents are often utilized as candidates in flow birefringence studies. Examples of birefringence. The phenomenon of birefringence occurs in non-isotropic crystals. Below are few examples. Laser crystals, including vanadate or tungsten crystals, belong to intrinsic birefringent. This is useful in observing a linearly polarized output without depolarization loss. The nonlinear crystals for nonlinear frequency conversion are birefringent. Birefringent crystals are also used for making polarizers. Straight optical fibers exhibit a small degree of random birefringence, which can disturb the polarization state of guided light over propagation distance. There are polarization maintaining fibers with strong artificial birefringence and are used for suppressing such effect. Quantification of birefringence. The magnitude of birefringence can be estimated in various ways. In bulk crystals, the difference of refractive indices for the two polarization directions is considered to provide birefringence. In optical fibers and other waveguides, the difference of effective refractive indices provides more appropriate to consider. This can be directly estimated from the differences in imaginary values of the propagation constants. In a waveguide, if the waves with different polarization directions propagate together, their phase relation could be restored after integer multiplies of the propagation bit length L subscript p is equal to 2 pi divided by the difference of propagation constants.
So students, let us summarize what we have learned in this module. The efficiency of nonlinear optical processes could be determined from the nonlinear susceptibility of the medium and the phase mismatch parameter. To achieve optical energy conversion efficiency, the phase matching condition, which is delta k is equal to 2k1 minus k2 is equal to 0, has to be fulfilled. These relations can be translated into relations between the refractive indices at the respective frequencies. For example, in case of SHG, phase matching requires N1 omega 1 is equal to N2 omega 2 with omega 2 is equal to 2 omega 1. Except for very specific cases, material dispersion usually does not allow to fulfill such kind of relations. The most commonly used technique of phase matching relies on utilizing birefrigerants. Birefrigerants is a phenomenon manifested by an asymmetry of properties that may be optical, electrical, mechanical, acoustical or magnetic in nature. A wide spectrum of materials display varying degrees of birefrigerance, but the ones with specific interest to the optical microscopist are those specimens that are transparent and readily observed in polarized lights. Thank you.